In this video, we are going to continue to talk about Aldol reactions, specifically cross-Aldol reactions. Understand that when we have two different aldehydes or ketones, they can react in a cross-Aldol reaction, in other words, a mixed Aldol reaction. As you can see in the slide, and I'm just going to focus on it, we have two different aldehyde molecules, and I'm going to label them A and B. Okay. In a mixed aldol reaction, you can envision a series of reactions happening in the vessel. In the first set, this is where we have A acting as an electrophile and A also being a nucleophile, forming an enolate. In the second set, we can envision B being an electrophile and B being a nucleophile because it's going to be forming an enolate. In the third set of reaction, A is going to be our electrophile and B is going to be our nucleophile, forming that enolate. And lastly, B is going to be our electrophile and A is going to be our nucleophile to produce the following products. As you can see, each one of the products that we have illustrated here is going to be that beta hydroxyaldehyde. So if we have specifically two different aldehydes in the vessel, as you can see, two different aldehydes will yield 4 possible aldol products. Understand that cross-aldol reactions are only practical if the number of products can be minimized, which is achieved by one of two ways. The first way is if we have a substrate that is relatively unhindered or without alpha protons, because what this is going to result in is that, as you can see, formaldehyde, since it has no alpha proton, that is going to allow the other aldehyde to act as a nucleophile because it can produce the enolate. So, as I mentioned before, when this is allowed, and as you can see here, we have benzaldehyde and propanol reacting with one another. Understand that having only one aldehyde with no alpha protons is going to allow the one that has alpha protons to create an enolate, and they will be able to react faster. Remember, when we have two aldehydes, as we learned previously, we are not going to be isolating the beta hydroxy, specifically if we have heat, and we're going to have the alpha beta unsaturated carbonyl system as our final product. Another way in which we can do a cross-aldol reaction is by doing a directed aldol addition. What this means is that we are going to take the specific aldehyde or ketone that we're interested in to be the nucleophile. We are going to react it with LDA, create the enolate, because as we learned previously, the use of LDA is going to prefer the formation of the enolate, and then we are going to be introducing the other carbonyl compound. Okay, once that occurs, then we have a directed way to form the product that we are interested in. Understand that in this reaction, we're going to have a workup in order to get the hydroxy, um, or sorry, the oxygen that is negatively charged form a hydroxyl group because it needs to be protonated. Understand that aldol reactions can also happen intramolecularly. And when that occurs, they are going to be forming specifically cyclic compounds. In these reactions, understand that one group is going to form the enolate and is going to attack the other group. It is very important to focus on the second bullet point. Only 5 and 6 member rings are going to form well this way. And the reason is, remember that each one of these carbon atoms that is here is going to have a particular angle. And as we have 5 and 6 member rings, the ring strain is going to be reduced in these systems. That's why 5 member rings and 6 member rings are preferred. Now we are going to proceed to talk about Claisen condensations. When it comes to Claisen condensations, understand that this particular type of reaction has to do with esters. Esters also can undergo, as you can see, reversible condensation, and this type of reaction is actually called a Claisen condensation. So when we have an ester reacting with itself, followed by an acidic workup, as you can see, you're going to form a dicarbonyl system in essence, in which one side is an ester and the other one is going to have a carbonyl derivative. And as you can see in this example, we have a ketone. That's why this compound is called a beta keto ester. So understand that a Claisen condensation is simply a nucleophilic acyl substitution reaction in which the nucleophile is the enolate of an ester, while the electrophile is going to be an equivalence of the ester itself. Now let's go over the mechanism for Claisen condensations. Remember, we have to generate first an enolate intermediate in order to attack a fresh new molecule of ester. So, as you can see, for accomplishing this reaction, we are going to have a base deprotonate the alpha proton on the ester. That is going to be producing an enolate of the ester. Then that enolate is going to attack at the carbon atom in the C double bond O of a fresh new molecule of ester. And what that's going to create is a tetrahedral intermediate that when the oxygen atom takes a lone pair and puts the electrons down, then we are going to be expelling out of the molecule an alkoxide as a leaving group. Now understand that now that proton, as we discussed previously, that lives in between the two C double bond O atoms, it is quite acidic. So in the presence of that alkoxide, that position is going to be deprotonated. Since it is deprotonated, remember that in order to regain that proton, that's why as a second step we have an acidic workup in this reaction. Understand that there are some limitations to the Claisen concentration. The first one is that the starting ester must have 2 alpha protons, because the removal of the second proton by the alkoxide ion is what drives the equilibrium forward. Then understand that hydroxide cannot be used as a base to deprotonate the ester in Claisen condensations. because as we learned previously when we were talking about carboxylic acid derivatives, the use of hydroxide, what is going to be generating at the end of the day is a carboxylate. Because what is going to provoke is that ester is going to undergo hydrolysis. Thirdly, understand that in alkoxide that matches specifically the OR group of the ester is needed, because if it's not utilized, then what is going to happen is transesterification. And in transesterification, understand that basically we are going to be exchanging, and I'm just going to highlight it in orange, the OR group in the ester for the OR group that was in our alkoxide. So again, when we're utilizing a base, it must match the OR group in our ester in order to prevent transesterification. Claisen condensations can also occur as cross-Claisen condensations, but understand that they're only useful if one of the following criteria is met. One of the esters must have no alpha protons, and as you can see in the reactions on number 1, in here, if we have different esters, then that means that specifically the one that it is in blue will be able to form the enolate that will then attack the carbon atom that is double bonded to the oxygen in order to produce the product that we see on the first set of the reactions. Understand that in order to perform a direct Claisen condensation, you can also utilize LDA as the base. If we utilize LDA as the base with the ester that we're interested in to utilize as an enolate, then we are going to, as we saw in previous examples for aldehydes, then we can incorporate slowly that second ester in order to accomplish the molecule that we have as a target. When it comes to Claisen condensations, understand that we can also have intramolecular Claisen condensations, and these specifically are called Dieckmann Cyclizations. Similar to what we've seen previously, when it comes to Dieckmann Cyclizations, the formation of 5 or 6 member rings, it is preferable. So as you can see in the example that we have on the slide, specifically, remember, in this system, we are specifically going to have carbon 2, and this is just because of the way that it is labeled. Carbon 2 is the one that is going to be forming the enolate and is going to be attacking the carbon atom that is double bonded to oxygen and carbon 6, and that's how we are forming specifically that 5 member ring that we have as a product. The mechanism for this is not any different than what we discussed previously when we were talking about Claisen condensations. It's just that it happens intramolecularly. Now we are going to move on to talk about the alkalization of the alpha position. We already talked about halogenation. Now, understand that the alpha position can be alkylated when an enolate is treated with an alkyl halide. As you can see in the example that we have in the general reaction, in the first step of the reaction, we're going to utilize LDA. That's what's going to be creating our enolate. In the second step of the reaction, we're going to have the introduction of an alkyl halide, and that's what's going to bring the alkyl group. So what you have in the bottom is just the illustration that alkylation is going to be occurring via an SN2 reaction. Now, remember from first semester, whenever we have SN2 reactions, we always have a little bit of restrictions that we have to keep in mind. Typically, SN2 reactions apply when we have secondary or tertiary alkyl halides. But then remember that at times, as you guys learned previously, E2 eliminations are going to dominate. So in the Aldol reaction, it also competes with the desired alkylation. So a strong base such as LDA must be used in order to form that enolate. Understand that regioselectivity, it is an issue if you have an unsymmetrical ketone, okay? Because what happens is that two different enolates can form. Here we have an example of what can occur if specifically you have a ketone atom, okay, that now it is substituted and it is not symmetrical. As you can see, the use of base is going to be producing two different ketones that are going to have their enolate intermediates. Now, as you can see, the one that it is on the left side, that one is thermodynamically the most stable enolate, because the carbon-carbon double bond that is part of the enolate system, it is more substituted than comparing it to the molecule that we have on the right side. It is interesting to note that the one on the right side, even though it is formed faster, it is actually less stable. In this energy diagram, this is just illustrating the path or the reaction coordinate diagram that illustrates the kinetic and thermodynamic enolates that are going to be forming in a solution that have an unsymmetrical ketone. This is just illustrating what is happening overall. But it is important to note that the kinetic enolate is going to be favored by irreversible conditions, meaning if you use LDA at low temperature, while the thermodynamic enolate will be favored by reversible conditions, meaning if you use sodium hydride at room temperature. So as you can see illustrated in the following example, depending on the type of alkylation that you want in your product, you may be leaning towards the use of LDA or the use of sodium hydride. So to recap, if the alkylation needs to happen at the less substituted side of your unsymmetrical ketone, then you are going to be using LDA at low temperature to incorporate that alkyl group. On the other hand, if you're trying to incorporate the substitution at the more substituted side of this ketone, as you can see where we already have an R group and we're trying to install the second one on that site, then the reaction that you should utilize is sodium hydride at room temperature and the incorporation of that alkyl group. Continuing talking about the alkylation of the alpha position, now we're going to talk about the malonic ester synthesis. And in the malonic ester synthesis is where we have an alkyl halide that it is converted into a carboxylic acid, okay, with two additional carbons. In a way, in this malonic ester synthesis, what we're doing is that we are, as you can see, alkylating part of the carboxylic acid. Now, understand that for this process, diethyl malonate is the starting material. Okay, so what's going to happen is that diethyl malonate is first going to be deprotonating, and as you can see, we're going to use the alkoxide that is going to match the OR groups in our ester. This is going to be a stabilized enolate because, as you can see, it is in the middle of two carbonyl groups. Then the enolate is going to react with the alkyl halide in order to incorporate the R group in between the two carbonyls. Then it is going to have an acidic workup to transform those esters into two carboxylic acids. So this is just going to be the hydrolysis of changing those esters into carboxylic acids. Towards the end of this reaction, as you can understand, there's a few more steps. And what's going to happen of that molecule that changed into the 2-carboxylic acid is that it's going to undergo a process of decarboxylation. In this decarboxylation, as you can see, what we're going to have overall is that, I'm just going to highlight it in green, this portion of the molecule is what forms, so what I highlighted in green is what forms that CO2. And that decarboxylation happens specifically when heat is utilized. As you can see, you're going to have an enol intermediate that then is going to tautomerize to form that substituted carboxylic acid. So understand that the overall view of the malonic ester synthesis goes as follows. In the first step of the reaction, remember that we are going to be utilizing our alkoxide in order to deprotonate our starting material. On step 2 is where we are going to have the alkylation process. On step 3 is where we are going to have it specifically formation of carboxylic acid on each end of our molecule, followed by decarboxylation. Now, understand that the diethyl malonate doesn't necessarily need to be alkylated just once. This reaction, the malonic ester synthesis, can be utilized in order to dialkylate our starting material, as you can see in the bottom example in this slide. Another useful reaction that has to do with the alkylation of the alpha position is the acetoacetic ester synthesis. This reaction is analogous to the malonate synthesis, in which we are going to convert an alkyl halide to a methyl ketone with 3 new carbon atoms. As you can envision from the set of reactions that we have here, in the first step of the reaction, what we are going to be doing is specifically the deprotonation of our starting material. So you can envision that now we're going to have the following enolate. On the second step of the reaction, then we're going to do the alkylation process. In the third step of the reaction, we're going to have the modification of that ester motif into a carboxylic acid, followed by decarboxylation. So in the decarboxylation is where we are going to be finally ending with our final product.